Hi there, Mr. Sutton here, bringing you the AB Calculus 6-7 Extra Practice number 5 solutions on total distance. For this problem, we have a referee moving along a straight path on the side of a field. Velocity of the referee is given by this v function here, very complicated velocity function for a ref, and we want to know the total distance traveled by the referee in meters from time 2 to time 6. So if we're doing total distance on a calculator, then we don't really have to worry about whether the velocity changes sign or not. We're just going to do the integral from 2 to 6 of the absolute value of the velocity. That way we don't have to worry about whether we're changing directions or not. So we're doing absolute value of v of t dt, and now we're just going to do this on the calculator. So here I am in the y equals of my calculator. I've entered this function in there, and now I'm going to quit out of there, and let me just do Math 9 to get my integral from 2 to 6, and I'm going to do absolute value. So let me do alpha window, pull up that little menu, and then abs is what I need out of there. And I'll do alpha trace to pull up the y menu. Y1 is what I want because that's where I stored v of t. dx, and let's see what this comes out to. So usually there's a little bit of a weighting involved with these integrals of absolute values. For some reason, it just takes the calculator a while. So we have 21.667, which is going to give us answer choice C. On this problem, we have a particle moving on the x-axis with this velocity. We want to know if our position at time 0 is x equals 3, which of the following down here tells us the position of the particle at time 2. So let's just go through each of these and see what we're dealing with. So for this first one, they're taking the integral of velocity from 0 to 2. So that's going to give us the total change in position, the displacement. Unfortunately, that's not enough to tell us the new position. I mean, knowing how much you moved is great, but you also need to know kind of like where you started. So this is a no. On to the next one, we have 3 plus the displacement that we were talking about in option A. And 3 was our starting point. So if I know my starting point and I'm adding the total change in position, then that will give me the new position. So this is a yes. This is probably what we're going to pick, but let's just look at these other ones. This next one, they're taking the derivative of velocity at time 2. Well, this is the acceleration at time 2, so that's a no. And then this last one, this is the absolute value inside the integral. So this basically displacement but absolute value. That's going to give us total distance, which is not the same as position, so that's a no. So then choice B is our answer. For this problem, we have a particle going along the x-axis, and they gave us the graph of its velocity. Over the interval from 0 to 8, the particle's displacement is 100 units to the right, and we're told the particle travels a total distance of 1,875 units. We want to know the total distance the particle travels while moving to the left. So we're differentiating between left and right movement. So I'm going to make some variables to represent this. Let's let r be the total distance I spent going to the right, and L is going to be our left distance. And since our displacement is 100 units to the right, that means, and you know, the right is the positive direction, that means that r must be bigger than L. So they gave us a couple pieces of information. This displacement piece of information, we can use this to write an equation with r and L, and we can also write another equation using total distance. That's what we're going to do in order to solve for L. So with displacement, we can say that r minus L is going to equal 100 because the L distance counts negative. The left distance counts negative when you're doing displacement. But now with total distance, we don't pay attention to positive versus negative thing when we're doing left versus right. It's all going to be positive distance. So for total distance, we can say r plus L equals 1875. And now I have a system of equations I can solve. If I add these two equations together, I have 2r equals 1,975. And if you carefully divide by 2, probably by hand here, I believe that comes out to, let's see, 987.5. Okay. Probably good to do that by hand, though. So that's not what we wanted. We wanted the L distance, but we at least got something here. So I'm going to plug this back into one of these equations now to solve for L. Now, between the two of these, I really don't want to mess with this 1875 number right here. So I'm just going to do this first equation. So I'm going to do 987.5 minus L equals 100. And now if I add L and subtract 100, I have L equals 887.5. So that's going to end up being choice B. For this one, velocity of a particle moving along the x-axis is given by this sine function here. And we want to know which of these expressions gives us the total distance traveled by the particle over the interval from 0 to pi. So in general, we're going to want some kind of integral to get total distance. But the million-dollar question is, can I just take the integral of velocity from 0 to pi, like they're doing in choice C, or do I have to split this up? I would have to split it up if I were changing directions somewhere between 0 and pi. So that's really the first question we have to answer is, are there any direction changes, any sign changes for velocity? So let me set this stuff equal to 0. That'll at least give me some critical values I can do some sign analysis around. And if I just divide both sides by -1, I have sine equals 0. So I can write t minus pi over 4 is going to equal, let's see, inverse sine of 0. That's going to be 0, and it also includes pi and 2 pi and all of those. But this is a pretty limited range here. So we're just going to include, well, actually, I'm just going to include 0, because if I set t minus pi over 4 equal to pi and then solve, that's going to give me something bigger than pi. So let me just say that t minus 4 equals 0. But keep in mind that there are many values where sine is equal to 0. This is just the only one that's actually going to allow us to get answers inside these endpoints here. So adding pi over 4, we get pi over 4 is our only critical value. So now let's do some sign analysis. We have endpoints of 0 and pi, and this is for velocity now. There's our critical value of pi over 4. Testing something between 0 and pi over 4. How about pi over 8? So I'm going to plug this into the original velocity function up here. Pi over 8 minus pi over 4, that's going to give me something in quadrant 4. I think it's going to be like negative 22.5 degrees or something like that. Anyway, sine of that would normally be negative because you're below the x-axis, but there's already a negative out in front, so that reverses our sign to be positive on that interval. And now something between pi over 4 and pi, well, pi over 2 is kind of the obvious choice here. But now plugging this in, we've got pi over 2 minus pi over 4. That's just pi over 4. Sine of that is positive, but then there's a negative out in front, so that whole thing becomes negative. So we see that there is definitely a sign change at pi over 4. That's telling me that my particle is changing direction at pi over 4. So I am going to need two integrals, and I'm going to have to make sure that each integral gives me positive area. So for this first integral, since velocity is positive, my distance that the integral gives me is going to be positive. So I just have the positive integral from 0 to pi over 4 of v of t dt. But now, this next integral is this is negative velocity, so it's going to end up giving me negative distance. So in order to offset that, I have to actually subtract the integral that comes out of this interval. So I have to do minus integral from pi over 4 to pi of v of t dt. And now that's going to end up giving me, looks like answer choice D. Yep, there we go. For this calculator-based free response, we have a particle moving along an x-axis with this velocity function between time 0 and 3.5, and we are at the position x equals -5 at time 0. So now they want, for our first task, they want us to find the acceleration of our particle at time 3. So we're asking basically for a of 3. Now to make a connection and actually get credit on this, you need to show that a of 3 equals v prime of 3, because we don't have an a function, but we do have a v function. And although I'm not going to show what v prime looks like algebraically, I'm not going to actually do the analytical version of this derivative. If I already have v defined and I just say, hey, I'm about to take the derivative of this at 3 on my calculator, I'm allowed to do that without showing anything else. So let me go ahead and do that now. So first things first, I have to actually enter the velocity function into my calculator, which I have done here in my y equals under y1. Quitting out of that now, I just need the derivative of y1. So that would be math 8 n deriv. I'll put a x down there next to the d, And now in here I'm going to do alpha trace y1, and then I'm going to evaluate that at x equals, actually in this case it's t equals 3, but they use x on our calculators. So plug 3 in there, and that comes out to negative 2.118. And there's no units on here at all, so we're just going to leave it at that. For this part, they want the position of our particle at time 3. So to get that, I have to get the starting position, which was negative 5, and I have to add the change in position, which is to say the integral of velocity from time 0 to time 3. So I can write x of 3 equals negative 5 plus the integral from 0 to 3 of v of t dt. I don't have to actually rewrite this whole thing because they've already defined what v of t looks like. So let me just do this on the calculator. So here's what I am plugging into my calculator. We have the negative 5 plus math 9 integral 0 to 3 alpha trace y1 dx comes out to negative 1.760. For this part of the problem, they want us to evaluate the integral from 0 to 3.5 of v of t dt, and then pretty much the same thing but with an absolute value thrown in. And then we have to interpret the meaning of each integral in the context of the problem. So part of the credit on this is just plugging it in your calculator. So let's go ahead and do that for this first one. So here's what that looks like on my calculator. Remember, I entered v of t as the y1 in my y equals. So I'm just doing the integral from 3.5 or 0 to 3.5 of that and pressing enter. That's 2.844. So what does that actually mean? Since I'm just taking the integral of velocity without any other bells and whistles attached, that just gives me the displacement of my particle from time 0 to time 3.5. So you have to mention displacement, and you also have to mention the time element in here to get full credit. If you just said displacement without mentioning the time, you would not get the point. Get the point? All right, so this next one now, let's plug this in the calculator. So just like before, I'm setting up an integral from 0 to 3.5. Now to get the absolute value, I'm just going to do alpha window and press enter on that first option, abs, and then I'll do alpha trace to pull up my y menu and select y1 out of that. And then let me do dx, press enter. And the integral of the absolute value version of velocity is going to give us 3.737. And what is that? Well, whenever you take the integral of the absolute value of velocity, you're essentially getting the total distance because you're not counting negatives against the distance acquired here. Every distance is becoming positive. So this is the particle's total distance traveled from time 0 to time 3.5. For this last part of the problem, we have a second particle moving on the x-axis with a position given by this function here, same time interval as before. We want to know at what time the two particles are moving with the same velocity. Well, I already have a formula for the velocity of the first particle. I do not have a velocity formula for the second particle, so let me go ahead and get that. I'm going to call it v2. v2 is going to basically be x2 prime of t, which is just going to be 2t minus 1, just using the power rule there. So I want to figure out when this velocity function equals my original velocity function. So I'm basically going to set these two things equal to each other on the calculator, or graph them both on the calculator, and see where they intersect. Let me do that now. So here I am back in my y equals. I've still got my original velocity function for particle 1 in y1, and now I've entered this 2t minus 1 function in y2. Let me go ahead and graph these, and I'm going to use a window from 0 to 3.5 because these don't apply anywhere else anyway. So 0, and we have 3.5 as the x max. And now zoom 0, zoom fit. Let's see if these cross anywhere. So here's my original velocity function for particle 1. And now here is particle 2. There's a nice little crossing right there, and there's only one. So let me do second trace, option 5, intersect, and we're pretty close. So let's just press enter, enter, and enter. And that comes out to about 1.571, which might even be pi. I'm not really sure. It looks like it's at least pretty pretty close to pi over 2. Close to pi over 2. But that's neither here nor there. We just have to round it off to 3 decimals, and we are done.